Okay, let's do this. Welcome everyone. How's the transmission? Can you hear me? Can you see me? Welcome to another Meyer webinar. Excellent. Thank you for confirming, Oscar. So today we have an interesting topic, coherence. So without further ado, let me go to the household notes and then hand it over to today's guest lecture. As I said before, today is going to be all about coherence, and we have a guest lecture which we'll introduce a little bit in a little while. Stay tuned, because first we're going to briefly talk about the Zoom video communication platform that we use to conduct these webinars. In front of you, you're expected to have a window not unlike the one you see right now. If you would like to see who else is joining you on today's webinar, please click on the participants button, in which case a window shows up to the right side, showing you your fellow attendees today. We encourage you to ask questions also during the session, but in order to do so, please make use of the raise hand feature. Notice that in the bottom right corner of the white window, there is a button called raise hand, and whenever you click that button, a blue hand icon pops up informing me that you're about to ask a question. At which time I will try to find a white space in the narrative of our guest lecturer and interrupt him to pose your question. In order to ask the question itself, we encourage you to make use of the chat function. Whenever you click on the balloon icon, the chat icon, the right-hand window splits in half, bringing up a chat dialog. There's a field at the bottom where you can enter a message, which you can then send to everyone that is joining us today. Or if you happen to see a fellow family member, a colleague or friend, then you can also address that person in private. As we speak, we're also simulcasting to the Meyer Sound Facebook user group. Welcome to you as well. We're streaming live as we speak. The Facebook group is growing at a steady rate, steady pace. Currently, it has over 8,900 members. So welcome to you as well. And that means that without further ado, I would like to see whether our today's guest lecturer, Juan Lozano, acoustic test engineer at Meyer Sign, is with us. Juan Sierra, are you there?
Hello.
Hello, we can hear you.
Microphone muted.
Thank you for joining us. How are you doing?
It's going. Just a little bit of running with all of this, but everything's okay.
Okay. Well, Juan Sierra is going to take us on an interesting journey called Coherence. So without further ado, Juan Sierra, it's all yours.
Okay, Dali. It's like people who always follow our webinars. Thank you for being around. Thank you all for joining us. This is an interesting topic. It's a tough one, but we'll see how we can make it work. So maybe some few notes before we start. This is a little bit of a math-oriented topic. I usually like to provide a very like conceptual understanding of things so that you can like grasp the real meaning of all of these topics. But in this case, it really requires a little bit of math to understand why this is actually showing as it is showing. Also a little bit of patience because I'm trying to move between two different computers. So at times I'll try to organize everything so that we can watch stuff on one computer for demonstration purposes and stuff on the other computer for the presentation itself. So let's see if we can do this. All right. If I do this, oh no, there's a little bit of a problem here. That should be fine. All right. So the topic of today, as Marvin said, is coherence. Once again, thank you for joining all of us and thank you for following all of our webinars. So let's do this. So coherence, and it says, if two signals are ergodic and the system that relates them is a linear and time invariant system, then the coherence indicates the causality between one and the other. And the end, that's the end of the presentation because that's all that coherence is, except that it's not that simple and that definition is pretty impossible to understand by itself. So let's dig a little deeper into that. So let's see if this works. Let's first do a quick check on linear and time invariant systems. Let's see if all of this makes sense. So some properties of time, linear and time invariant systems. Oh, I'm gonna go here. All right. So some properties, the first proportionality means that some signal X that goes through a system L, which produces an output Y, the scaled version, the multiplication of X by some factor, would produce an output that is scaled in the same manner. So that is a proportionality property. Then we have additivity, means you can sum two different signals and pass them through a system and obtain two different outputs, and that would be the same as passing the sum of the original signals as the input of the system. Then we have linearity, which is what just a connection of the last two, meaning having scale values for the individual signals, summing them, and having an output that should also be well behaved. And finally, invariability, which means that if you feed the signal at a different time, the system should react in the same manner. So this is the idea of a linear and time invariant system. That is why it's LTI. And that is the basic thing that we're sort of trying to measure with all of our transfer functions and all of these system analysis. So having that understood, let's check a quick thing about the convolution theorem. So the convolution theorem is just the idea that a convolution, which is a mathematical operation, um, in the time domain between signals A and H, says the okay. Let me grab just one thing so I can write over here. Okay. So so the convolution between A and H will produce a signal B. And the convolution theorem says that if you have those signals in the frequency domain, then that is the product of A and H, and it will be the result will be the Fourier transform of B. So all of these guys are Fourier transforms related. So this is the Fourier transform of these. This is the Fourier transform of these, and then this is the Fourier transform of these. And interestingly enough, the convolution theorem calls in both ways. So a product in the time domain is also a convolution of their spectra. I think that's a pretty interesting thing that is not, it's often overlooked, but it's an interesting aspect of it. All right. So those are some of the basics that we need to understand to get into all of these topics. I know if at some point any of you want to know a little bit more about these specific ones, let me know. You can ask me on Facebook at any time or later on the webinar or something, but let's go deeper into the analysis of systems. So a description of a system, uh, it's an interesting thing because it's different than what we think that is the measurement of a system. A description of a system is understanding how the system behaves, and it's analyzing sort of its input and output relationship in what is known as a black box approach. We don't understand how the system is doing what it is doing, but we know that it is actually doing it. So in this black box approach, we sort of know that the system that we're analyzing has these properties. In this case, we feed a signal A into a system H, we get an output B. We relate those through the Fourier transforms and we get the spectral versions of those. And we can sort of solve for H in this case. And we can say, okay, we need to know this guy, so we're just gonna move this guy over here. And by doing that, we get a definition or a description of the system, which is H. We can even go further and take the inverse Fourier transform of that and obtain the input response. That should be like, I feel like people should have some relation with all of this and have some understanding of all of this. But the interesting thing becomes when you, oh, okay. So first, let's try to understand a couple of things about visualizing transfer functions. Um, so the visualization of transfer functions is an important part to have like good decision making on what we're actually doing. So we usually check the frequency versus the magnitude and the frequency versus the phase. That is sort of the common way to understand all of these things. but there's a bit more to all of that. So let me show you guys. Uh, I'm gonna do display capture. Whoops, a little glitch over here. Just a second. Transform. All right. Whoops, 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 whoopsie. Okay, this should work. Can you guys hear, see all of this, right? So let's see. Yeah, so we usually know these ones. Real part versus frequency is not that common. Imaginary part versus frequency is not that common. We really know the magnitude versus frequency and phase versus frequency, which is what we often see on measurement systems as smart. We don't usually see real versus imaginary. It's also a little bit common, and we obviously know impulse responses. Zero pole diagrams, not that much, but all of these are representations of transfer functions. And what I want you guys to see is, let's check the real versus imaginary versus frequency. So it's a 3D plot. I'm gonna represent in this 3D plot a parametric filter. And in this parametric filter is gonna have, let's say, 6 dBs of gain at 1000 hertz or close to that. Doesn't need to be exactly that. So it's pretty weird what we're seeing. I believe that is not that common for people to see transfer functions as represented in this way, but it's gonna be useful later. So if we check the actual transfer function, this is what we're used to see, is the frequency response and the amplitude response and the phase response. They are both on this top plot. And what you're gonna see is that the phase is going to increase and then decrease to some point. So we need to think about that as a line that is moving at 0 degrees, no inclination, then the inclination increases, then decreases to 0 at 1000 hertz, and then decreases again. Let's see if we can make sense out of that. So in the complex part, in this 3D plot, we're seeing exactly that. If you see that the inclination of this vector is increasing and decreasing, I'm going to use this analysis frequency to show those. So the angle of that vector is increasing, then decreasing, and then comes back to 0. So this odd shape is sort of the same as this one. It's just that in this case we're representing the magnitude and the phase, and in this case we're representing the real versus the imaginary part versus the frequency. And it sort of makes sense, like the phase doesn't change that much, so the angle that measured against the horizontal axis should sort of start at 0, then increase a little bit, at 1000 hertz becomes 0, and then decrease again, as it is shown by the transfer function. Hope this is making some sense. And then again, this is just the visualization of this same plot by like seeing the depth of it. So these two plots are almost identical. It's just the projection on the depth field of this 3D plot. And then you can see other types of filters, like an all-pass filter is just the magnitude of that vector is always unitary, it's not changing, but the phase is always changing as it is shown by the transfer function. So the phase starts here and decreases at 0 at the Nyquist frequency. And that is sort of the same thing that is happening here. If you increase the order of the all-pass filter, then you get more rotation. So it sort of makes sense that this is what it is doing. All right. I wanted to show all of this because this is how we're gonna need to understand why coherence is what it is. So let's go back here. So it is a good exercise to try to understand all of these representations of transfer functions. So in this case, we're just gonna use that one, and we're gonna try to see how the description of a system is different than an estimation of a system. So the problem arises from what is known as numerical methods. So numerical methods are like directly from Zoom, the resolution is only 640 by 360. Let's see if I can try to help with that. So Marilyn is saying that the resolution might not be enough for reading. Let's see. It's better?
Major improvement, much appreciated.
All right.
Thank you very much.
When symbolic structures can't be solved, which means like the equations themselves, like the formulas that we use to do all of these calculations cannot be solved by a computer, then we use approximate solutions. And these approximations are like a field of mathematics that is known as numerical methods. It's a very important part of computation because a lot of things cannot actually be computed on an actual physical computer. Like the square root of 2 only can be approximated because it has infinite decimals. And actually, this is like a Babylonian tablet that is showing like an approximation of the square root of 2 and some calculation based on geometry, and showing, okay, we can use some numerical method to get to this information. And it's important to understand that often we don't calculate these things. We really estimate them because we're actually doing like an approximation process to get there. So what is this approximation process in this case? So I know that often people have shown you guys like you divide the input by the output and that is the transfer function, but that is not at all how the insides of transfer function measurements go. So this is a little diagram. I encourage you guys to take a screenshot of this and hold it for the rest of the presentation. It's gonna be pretty useful later. So we have a two-channel measurement system. We have a time buffer. We store like 1024 samples of audio. And then we're gonna do some spectral transformation. We do a Fourier transform of that to get the spectral buffer here. And we can compute the cross spectrum, which is gonna be an interesting concept that I'm gonna dig deeper later. We also have the self spectrum, which is again something that I'll explain in detail. And from the self spectrum and the cross spectrum, like these guys, compute the frequency response. Interestingly enough, there's two estimations of the frequency response. There's an estimation called H1, an estimation called H2. And the coherence actually comes from the ratio of these two estimations. If we go back to the time domain, there's a point where we can calculate the self-correlation and compute the cross-correlation, which are time domain inverse Fourier transforms of self spectrums and cross spectrums. So I know this is getting a little bit crazy at this moment, but let's take it like a step at a time and let's figure all of this out. All right, so just keep in mind all of this graph to understand what is going on later. All right, so we really want to get to this guy, coherence, so we're gonna jump into it. So the self spectrum, we say that is the square of the magnitude of the spectrum. It is like the product of the spectrum with its complex conjugate. That is what this over bar means. And this is just the representation of the Fourier transform. What I want you guys to see is that in the, oh, sorry, these two labels are in Spanish. Symbolic analysis and numeric analysis says here. All right, so this is saying that we need to compute the spectrum from an infinite length time domain signal. But as I said, in the numerical analysis, we only have access to limited amount of information. So the relationship in here is just gonna be a specific time 1 and time 2. And because it is going to be limited, then we cannot say that it is actually the self spectrum. It's just an estimation of the self spectrum. And that's where these things start to become important. This is a representation or the mathematical function known as the expectation or the expected value. And accordingly, this little hat on our variable that represents the self spectrum is going to represent an estimation of the self spectrum. It's not going to be actually the self spectrum, but something that is going to be close to it. And that's actually where all of the mess starts. So why do we need to take an infinite amount of time? Well, because a lot of people will say very often in a light way that noise has all the frequencies, and that is actually not the case. Noise has a what is known as density spectrum, or a spectral density that is that converges to all frequencies, meaning that through all time all the frequencies will show up on average the same amount of time. But it doesn't mean that at a single buffer of frequencies of time samples, all of the frequencies are present. And I'm gonna show that on this animation. You're gonna see on the top the actual immediate spectrum and below the power spectral density. So the power spectral density converges to flat, which means this is a white noise signal, but the spectrum or the squared spectrum has random spectrum actually. So because of that, we cannot actually use this noise and expect that at every moment all of the frequencies are going to be excited. We can only expect that to be the average behavior, or the estimated behavior, or the expected behavior. So it is important to understand that noise doesn't actually have all frequencies, but it's the spectral density converges to that. And to prove that, I am showing here that I was producing blocks of 1024 samples and analyzing each spectrum. And then I was asking, is any of these frequencies lower than minus 20 dBs, less than minus 50 dBs, less than minus 80 dBs? And how many blocks do I need to compute so that there's a random chance of at least one frequency being below that threshold? In this case, here I'm asking, is any frequency below 50 dBs? Yes. After two iterations, so the second block that I computed, at least one frequency was below 50 dBs. And if I go to a lower and lower threshold, then I need more and more blocks to get, by chance, a frequency that doesn't exist on that block. After, if my threshold is 100 dBs, then I would need, let's say, 2,000 blocks before at least one frequency or at least one beam doesn't have any energy, showing that that noise doesn't actually have all frequencies every time. It is just a random, or technically it's an stochastic behavior that has some average behavior, but at any given instant is still random. So because of that, we cannot actually use that to analyze and measure all of these things. We need to average through time and do estimations of the system to understand its actual behavior. Let's see, what? This is the expectation, or what is it? Okay, so this is what we will actually average. This is the representation of the transfer function as real versus imaginary versus frequency. And it is actually the representation of that parametric filter that I was showing you guys before. And because all of these are estimations, the estimation is not perfect and converges to the actual behavior of the system, but only after a lot of averaging. So this plot is going to show what is actually happening on each of the measurement blocks. So you should see that these blue lines represent the values of the transfer function, and they're sort of jumping around. And I'm doing a quick zoom on only one of those, on the red red frequency over here, and this is its actual travel time. So it goes across, like, during all the measurements, it's jumping around certain point, and that is what we're going to average. The estimation, or the correct estimation of the transfer function at that frequency, is going to be the average of all of these points. And when we do that, then we can compute coherence, because coherence comes from the quality of the estimation, or how that measurement is changing over time in its statistical behavior. So I'm gonna run this animation again, because I think it shows a lot what we're trying to do. So make sure you understand that all of these blue lines represent the transfer function, real, imaginary versus frequency, and that they're jumping around slightly in the real and imaginary axis, showing some deviations from the real value. So over here is just an extract of this single red frequency, and here is a zoom version to show how this error is behaving through all of this time. All right. Oh, no. So the expectation. So this is, I don't want to get too much into the statistical details of all of this. So in a few words, the expectation is, let's think it about as the average. However, there's an interesting twist to all of this is that we often only know the typical average, the arithmetic average or the mean, but there are other types of averaging things around. So we also know what is known as the generalized mean. I'm gonna explain that a little bit more in detail. And the expectation is actually some generalized mean weighted by the probability of some event. In this case, the expectation of a roll of a dice is 3.5 because the average of 1, 2, 3, 4, 5, and 6 is just 3.5. And the interesting thing about the expectation and what we need to understand for the purposes of coherence is a little bit complicated, and is the fact that only ergodic processes converge to a mean. That means only a process where the long-term statistics match the analytical values of the statistics, um, when they meet, when they converge through time, that is an ergodic process. It shows that certain random processes, even if you average them through infinite time, they're not going to converge to anything. And one representation of that is sort of, if you throw a coin, on average you'll have half times heads and half times tails. But if you toss a coin and if you move right if it's heads and if you move left if it's tails, you don't converge to the center. It is possible that you start to deviate from the center, and it is not actually going to converge in an ergodic manner to the actual expectation of the process, because the expectation is still zero. You would still on average be in the center, but at any given time you could be in any position, and it's not more likely that you are exactly in the center at some point. So it's just a quick example of ergodic processes. Whew. All right, so sorry, this keeps happening. I check all of the titles and everything, and then I see things in Spanish. Sorry. So this is a little bit of the dark side of averaging. And what we know is the arithmetic mean, the typical average, is just summing and divided by n. That's so good. But there are other geometric or other types of means. So one interesting one is the geometric mean, which is the product of things and the square, the nth root of that product. It's going to have an important relationship with all of what we're trying to do. There's a harmonic mean, and this is not very common on these type of things, but you should see that as, for example, what happens when you're trying to compute the equivalent resistance of a parallel set of resistors. The harmonic mean is actually the equivalent resistance of all of that. And then there's the big or the great generalized mean, which is just this big chunk of math that it says literally sum and raise all of that to some power p, divide by n, and then take the pth or the p root of of all of that. And if you see that if p is 1, if p is 1, then it becomes the arithmetic mean. If p is exactly 0 by some crazy demonstration, it becomes the geometric mean. If p is exactly -1, it becomes the harmonic mean. And other interesting ones, as if p is 2, then it becomes the root square, the RMS value, the root mean square. So it's interesting to see that there's a generalized version of all of that. All right, so let's this is a little bit of a crazy thing, but you're gonna see that this is going to show up on all of these measurement systems, and it is to do a rectangular FIR filter is the same as averaging things through time. So taking the average of 4 values, as it is doing here, the current value plus the last value plus the last value plus the last value divided by 4 is their arithmetic mean. And that is exactly the same as filtering the signal with an FIR filter with a rectangular impulse response. So that rectangular impulse response, which is going to be 4 ones, well, 4 ones divided by 4, is the same thing as that. Then we have things like the cumulative mean, which is sort of taking the old mean, multiplying it by n, and then summing the new value and then divided by n plus 1. So that is sort of appending a new value to our mean and keep accumulating that. And that is what we often use when you say select something like a cumulative averaging on SIM or any of these measurement devices. And then we have like an exponential mean filter, which is an IIR filter. It is followed by this difference equation. And the interesting thing is to understand that as I'm gonna stop the screen share for a second. I want you guys to see sort of, so you have like an initial value and you have a new value for that. And instead of moving all the way up to there, you're gonna move only, let's say 10% of the distance. So this is the current value, a new value goes here, you move only 10%. And then you go to a different new value and then you only move 10%. So it behaves a little bit like an stability filter or a low pass filter that is sort of like is being able to average the typical behavior of a signal. Wait, what? I want to share this thing. Okay. All right, so, and that is what this equation is saying, is sort of the new state is going to be the difference between the new state and the old state multiplied by 0.1. So this is gonna move 10% away from the old state, 10% of the difference. And that is actually what we use when we select things like estimate average through 1 second. So it is sort of calculated in such a way that the newer values get more weight, the older values get a little bit less weight, and the sort of the average estimation time is 1 second. A lot of this is a lot for reference for you guys to check later because it's not like it's something that is a little bit hard to grasp, but I wanted to share all of this information so that you can check it out in different circumstances. Or ask me later if you have any question. So and the other means, well, we average to do two things. So that's sort of an interesting analysis of all of this. Is we average to make an ergodic process converge to zero. That means if we have some noise or contamination in our signal, we want to make that thing to converge to nothing so that it doesn't have any effect on the measurement. But we also take averages of things to understand the average behavior of a dynamical system. It means like if the system is changing through time, we want to understand what was the average behavior. And in that sense, it becomes very important to understand how different means affect all of this. So which mean is right? Well, it depends on what is your intention. And as I said, because the coherence comes from the ratio of two different estimations of the transfer functions, and the transfer functions are estimated through the cross spectrum and outer spectrum or self spectrum, then these two things, which are computed through estimations, through averages, are going to define how the coherence is going to behave. So this is a little bit of something that even Merlin has talked about in the past. So an arithmetic mean of these two vectors, let's say this is vector, this is vector 1, and this is vector 2. And the arithmetic mean of this is 0, meaning this is the value plus 1, this is the value minus 1, plus 1 plus minus 1 divided by 2 is just 0. And that makes a lot of sense. But in some other definition, we might be interested in understanding more how the phases and the magnitudes are related, for example. And the geometric mean is a good solution for that because the geometric mean is 1 times -1, so that is -1, and the square root of -1 is the complex value I or J, depending on engineering or mathematics. So if you have that, then the geometric mean is sort of behaving as the mean of the magnitude in dBs and the phase separately. So in this case, the magnitudes were the same. It was averaged to the same magnitude, and the phases were 0 and 180, and the average became 90 degrees. So there are different strategies to average all of these transfer functions to obtain different behaviors. And that's why I'm trying to explain all of this. So what's the deal with the coherence? So here I'm presenting yet again the same transfer function of a 12 dB boost parametric filter at 1K, just a common filter. And as you can see, I'm showing the arithmetic, geometric, harmonic, and P2, which is the RMS, the root mean square estimation. And in this case, well, they all have exactly the same value. So it doesn't seem like there's anything important in that. And that is because the measurement is completely clean without any contamination at all. But the way we average changes everything when the coherence is not exactly one, or when there's something that is sort of affecting the measurement of the system. And that is exactly this plot. So as you can see, the arithmetic mean is showing some uh, value over here that is a little bit below, let's say around 6 dBs, and then there's the harmonic mean, which is around here. There's the P2 mean that is around here. Oh, sorry, in this case, the harmonic and P2 are inverted. The legend is incorrect. I'm pretty sure this is the harmonic, and this one is the P2. And the geometric one is 0, and it's an interesting one because the way the system was contaminated was that I provided one block of this filter boosting 12 dBs and one block of this filter attenuating 12 dBs. So it was shifting positive, negative, positive, negative, positive, negative. And then the geometric mean actually showed the average behavior of the system. That was actually what we intended. So let me share this other screen for a second. Um, Can you spotlight my other video, Merlin? Okay, so you guys are seeing that one, right? And what I want to do is...
Juan, we have the same challenge. Can you screen share this rather than...
You prefer the screen sharing?
Yeah, because we lose all the
Yeah, of
valuable
course.
pixels.
All right.
Excellent, much
Okay.
better, thank you.
So here I'm just showing a measurement of a transfer function. Not that big of a deal, but what I want to do is to change the amplitude of a parametric filter in the way that I showed before. So that should sort of do the trick. Or not. Sorry. Okay, that should work. And I'm gonna do no averaging at all. So you can see that it is jumping from positive 12 dBs to negative 12 dBs. And let's set this to complex.
Juan, can you
And let's
optimize for
see.
video clip in this screen share?
Yep.
Much appreciated.
So you can see that that filter is changing plus 6 dBs, minus 6 dBs, and switching back and forth. And when you do the averaging through time, let's do infinite amount of averaging, you're gonna see that it converges to some value. And that value is actually, in this case, it's not a very good representation of the system, in the sense that it is not doing a geometric average and it is not computing the average behavior of the system. Obviously, these methods are not intended to measure dynamical systems, but linear and time invariant systems. So I'm sort of cheating on this one. But what I want to show is how like averaging is an important aspect of all of this, and how that is fully determining how the coherence is being computed and what is actually happening in this case. And I actually have another system running at the same time. So this one is converging, and it is actually converging to a different value. If you see this guy, this is at 1,000 hertz. It is showing an amplitude of 7.7. And actually, let me just share the full desktop so I can switch back and forth. So this is 7.7, and on Smart, it is converging to a different value. This is converging to 6.3. So it shows that the averages are being different. In this case, Smart is just doing an arithmetic average of the transfer functions. And the other software, which is called SpectraFull, the names are not very relevant. It's just to show how these things are different across different systems. It is showing an average of 7 point something, which is actually using the P2 mean. I also have a good friend, Oscar Barrientos, on Mexico. I'm sending him a couple of signals, and he should be able to show us, if he shares his screen, these same measurements on a scene. So this is showing the same, as you can see, the instantaneous values are switching back and forth between positive and negative. And the signal is, the transfer function is converging to some value. Can you show the cursor on the peak of that convergence trace? Yeah, so I'm seeing something like 6.2. And that is, again, what the arithmetic average would give. So it's interesting to see that all of this is changing, as you can, even you should see to some extent that the coherence traces could be slightly dissimilar because of all of these differences in the way that things are being averaged out. All right, so let's go back to our presentation, and then we'll come back for a little bit more of demonstrations. As I said, a little bit of patience because I'm sharing between multiple things at the same time, but it's going sort of okay. All right, so let's finally, let's start with this. An important disclaimer. Um, Signals in the time domain, which are often functions of t, and of frequency domain, which are functions of omega or frequency. I'm just going to represent their single letters without the independent variable, just because it's going to be a mess if all of the math comes and goes with all of these independent variables. So just keep in mind, A of t is A, and capital A of omega is A, and this is the cross spectrum AB of omega is going to be the cross spectrum AB simply. All right. So the first estimation, let's do this. So we multiply the input and the output by the conjugate of the input. In this case, we have the typical estimation. The typical definition of the product of these two spectra is going to give the output spectra. And multiplying all by the conjugate of A, which is the self-spectrum of A, is going to be what we're going to do in both sides. Then we take the expectation of all of these, and then here is exactly where the averaging happens. And then we solve for H1, and that is going to be our first estimation of H. Is going to be the first transfer function. Right, that's not that bad. All right, let's see our second estimation. Our second estimation is going to be multiply the input and the output by the conjugate of the output, of the output, of the output. All right. And when you do that, you're just gonna multiply by the conjugate of B. You're gonna have all this expression. This is the cross spectrum between B and A. Here, cross spectrum of B and A. And solving for H2, you're gonna have that is going to be the self spectrum of B over the cross spectrum of BA. That makes some sense, all right? So, if we go to coherence, finally we're there. We have the same thing. If two signals are ergodic and the system that relates them is a linear and time invariant system, the coherence indicates the causality between one and the other. Again, in this case, we already understand that ergodic means that the long-term average converges to something. And linear and time invariant systems, we sort of have a better understanding of what are their properties and everything. Now, let's see if this makes more sense now. So the coherence is, we can estimate it as the ratio between the first and the second estimation that I showed you guys before. This is the first estimation, this is the second estimation, and if we do this kind of trick, we sort of multiply these two and multiply these two, blah, 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 and everything's good and nice. Now, let's see what happens if we expand this in the original factors that compose those expressions. So A conjugate by B times B conjugate times A over A conjugate A times B conjugate of B times B. And we have sort of this A conjugate, and B, and B conjugate, and A and A. And sort of everything crosses out. So how is this even possible? Like the coherence should be one, isn't it? Like, oh, sorry, it should sort of be one in the sense that, oh, almost there. Okay, in the sense that it seems like the math is showing that everything should cancel out and everything should be okay. And the reason why it is not one, it is exactly because those are not exactly the cross spectrum and the self spectrums. They are the estimation of the cross spectrum and the estimation of the self spectrum. And that estimation occurs through the expectation or the expected value of themselves. Now, why is this not one? That is the question about coherence. The question about coherence is always why the estimation of the self spectra and the estimation of the cross spectra do not converge to the self spectra and the cross spectra. It means, why are these two things different? This is the symbolic representation of that, the perfect definition of infinite time, and this is an estimation of that value through a finite amount of time. And then understanding why that happens is what is going to lead us to understanding why coherence is not one. All right, so typical cases, and this is pretty, like I would expect people to be in this sort of type of webinar to have some understanding of these things, like contamination on a transfer function measurement is going to drop coherent because anything that is not part of the linear and time invariant system is just going to not converge properly through those estimations. So if there's noise, which is a degradation of the signal that does not relate to the signal at all, it's just an external thing that is sort of present in the measurement, but is not part or defined by the signal itself. That is going to be a problem. And distortion, which is a degradation of the signal that depends directly on the signal, is going to affect the measurement in a different way as well. So that is sort of like, okay, this is how things get messed up and why the coherence is not one. And this is why the estimation is not one at the end. All right, prepare yourselves. So what happens when there's output contamination? Depending on the estimation used, these might converge or not to the correct description of the system. Remember that we have this distinction between the description, which is the perfect definition of the system, and the estimation of the system, which is just um, some numerical method that is trying to approximate the description. And in this case, we have sort of a noisy signal. This is the system that is, the output should have been uv of t or v of t, and then we're adding some noise n, and we're getting our signal is actually becoming b of t, which is the sum of n and v. So how are all of these things changing then? Well, the cross spectrum of A stays the same, it's not a problem. The cross spectrum of AB is going to change, but because there's no relationship between A and N, between this and this, because it is just noise that is uncorrelated in any way with the signal, then it is going to be fine. And then we have the self spectrum of B. These were the three things that we needed to compute both the first estimation and the second estimation, and accordingly to compute the coherence. And this guy is messed up because now B, our signal, is the sum of V and N. And because it is the sum of both of those two, then we get some additional factor over here these cross products are canceled out because they are not related between each other. So the cross spectrum converges to zero. Um, and in this case, the self-spectrum of B becomes the self-spectrum of V plus the self-spectrum of N. And that is sort of why the coherence is not one. So, okay, this is, again, quick show up of these things. This is the self-spectrum of A, which is fine. This is the cross-spectrum AB, which is also fine. And this is the self-spectrum of B, which is not fine because it has an added value, which is the self-spectrum of the noise. So the fundamental relationships changed in a way that is not very pleasant. And we're sort of crazy because this shouldn't be happening, but it is. So the first estimation converges correctly because it didn't use the self-spectrum of B, so it is fine. But the second estimation, it is known to be overestimated. This overestimation is showing like an additional factor of H. It should have been H, but it is H times something that is bigger than 1. And because of that, we know that this is going to be overestimated. Because of that, again, the coherence, which is just the ratio between H1 and H2, between these two guys, is going to be, well, just solving some math around here is just exactly this term. Becomes this term, and then it becomes SVV over SBB, or the self-spectrum of V over the self-spectrum of B. And in that case, the coherence is going to be smaller than 1 because this factor is smaller than 1. And, oh, forgot again about the little blocks showing all of this. Okay, there we go. So that coherence is very interesting, and that is usually the coherence that we're talking about, because that coherence is just going to be this factor. And if we multiply that factor by the self-spectrum of B, which we have, then we can talk about the coherent power. And if we multiply that by the self-spectrum of the noise, no, sorry, if we multiply 1 minus the coherence times the self-spectrum of B, which is what we have from the measurement, then we get the non-coherent power. And it's an interesting property that we can sort of collect back what we were intending to actually measure. Even though we don't have we have a contaminated signal, we can sort of recover the self-spectrum of UV, of V, which is what we actually wanted, the output of the system. And that is why we call the coherent power, and we say, okay, the coherence is the ratio between the coherent power and the non-coherent power, but that is only in this case, that is only in the case where the output is contaminated and where it is actually contaminated with uncorrelated signals, uncorrelated noise. And that is a sort of a big assumption. So finally, because that is exactly as VV is the signal and as NN, or the subspectrum of N, is the noise, we can talk about the signal to noise ratio. That is what I was saying about like understanding the coherence as the coherent power over the non-coherent power. All right. So everything okay? Everybody okay? Everybody's alive? Nobody, haven't lost anybody? Everything fine? All right, so the other side of it is what happens if the input is contaminated, and that is sort of a no-no situation, but it sort of happens sometimes. In this case, the second estimation is which is the one that is, oh, sorry, here it should be first. Oh, the first estimation is underestimated, and the second estimation converges correctly, and that is sort of fine. And then the coherence is computed as I'm showing here, but the coherent power and non-coherent power do not apply because the contamination is not on the output, it's on the input of the system, or the input of the transfer function measurement. And it is sort of a tricky situation to do the same, to get to the same conclusions about coherence in this case, because simply the math doesn't follow that same way. Like, it is no longer the ratio between the output of the system that is linear and the part of the system that is noise. So the first estimation is a little bit underestimated. The second estimation converges properly because it doesn't use self um, the self spectrum of A, which is the one that is contaminated, is the one that it has some addition of noise M, and the coherence it represents the signal to noise ratio, but in a different way because it represents the signal to noise ratio in relationship to the noise that was introduced into the measurement, not into the system. Like the system is not actually processing that noise. As you can see, the noise, which is this M, is not going through the system. It is a contamination that is not part of the system itself. The system is clean. The thing is that the thing that we get to do the measurement is not. So it sort of is the signal to noise ratio, but not in the system sense, but more in the measurement sense. And then you can have a combination of those where you have contamination on input and output, and then you say, well, the estimation is the first estimation is underestimated and the second estimation is overestimated, which means that they are sort of bounding the real behavior of the transfer function. And it's a little bit of a shame that none of these softwares show the second estimation. They all show the first estimation because it also gives you interesting information. You sort of understand the overall behavior of a system by checking both of them at the same time. And you sort of are able to do that. It's just that it's not very common to do that type of analysis in depth. And the coherence, again, detect contamination, but it cannot be used to calculate anything in particular because it is sort of affected by both sides equally, and it depends on the levels of contamination on both of them. So the coherence is not actually showing the coherent power cannot be computed, cannot be used to compute the coherent power or the non-coherent power. It is simply a measurement of the degree of linearity of the system. It shows it's like a good reference point to understand the quality of the measurement itself, but it is not super useful to estimate other things like signal to noise ratio and stuff like this, because it is hard to separate all of this math and see like, okay, this is gonna perfectly fit in that definition. Okay, so let's check a quick example. I feel like we're running out of time. Is it okay if we extend a little bit? I feel like this is a very long topic. It's a little bit hard to.
All is good.
All right, let me share this other guy. Maybe can we do it with Oscar? I like to see things in Sim. I feel like Sim is pretty well built in this sense. Oscar, can you share a couple of okay, so in this case, we're not gonna measure this oscillating system. We're just gonna measure a fixed system. Okay, so now we have a very, very clean measurement. And what I'm going to do is introduce some noise in the output of the system. So there you go. There's some contamination on the signal. Am I getting too loud? Or everything okay on your side, Oscar? All right. So I'm introducing some contamination, but because this signal is completely uncorrelated with the measurement itself, then you can see that it's interesting that the measurement is actually pretty good. Like it is exactly what it is intended to be. That is the first estimation. We're contaminating the output. And the coherence is showing to some extent a very good relationship with the signal to noise ratio, in the sense that because the signal is louder where the filter is increasing the gain, the signal to ratio, the signal to noise ratio is better at those frequencies. So the coherence is better. So all of this makes some sense. Keep in mind that we're not even starting to talk about like multi-time window FFTs and stuff like that, which is a mess in itself, but this is a good estimation. Can you save that one, Oscar? So this is contamination of the output. Everything's good. Now let's let's invert the system. So by inverting the system, we're sort of seeing the second estimation and using the reference point as the process signal is going to the reference point, and I'm sort of changing the cables around. And this is a trick that a lot of people do. They think that it's pretty okay, but they don't realize the importance of this or the effects of this. So I'm gonna again contaminate the output, and this measurement seems fine. But if I do this, I'm contaminating the output. Can you reset the averages, please? Um, so now the coherence is sort of a tricky thing because it is not really expressing the signal to noise ratio in the measure in the device itself. Like the coherence should change in that position, but it's pretty flat. So it's sort of a tricky thing. It is describing the signal to noise ratio in the measurement sense, but not in the system sense. So can you save that representation? As you see, the transfer function still converges properly. So it is an interesting property. Uh, so those two are opposite of each other. It's just that because of the way we're measuring and where the contamination is going, the 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 measurement is behaving differently. Okay. Now let's go here. Again on a clean measurement, and I'm gonna contaminate the input. We have plus 12 dBs on that one. And this is where it becomes really interesting. So now the coherence is converging properly to some value. Again, this is more similar to the previous case where the coherence is not showing properly like the signal to noise ratio of the output in the output sense. But again, the estimation is underestimated. That is what is meant by that exactly. That you see that the value at DC or at Nyquist frequency is lower. It should be something like 6 or 9 dBs lower. And all of this is happening because of the way the averages are happening and all of that. So there's an underestimation of the transfer function, specifically on the magnitude part. As you saw, the definition of the or the part where I described the underestimation, it was a real factor. So the relationship between real and imaginary didn't change. So the phase is correctly estimated. It's just it is changed in the magnitude sense. All right. So can you save that one? And finally, I'm going to again sort of swap the cables so that we can see the second estimation, and I'm going to contaminate the input. So in this case, we have a clean measurement that is supposed to be 12 degrees below because now the reference point and the measurement point are swapped. But if I contaminate the input, okay, there you go. So it has a crazy behavior in the sense that the measurement is both underestimated and the coherence is sort of it's acting in a funny way in the sense that the signal is lower at that point, but the coherence is better. And that is because our reference is not it is sort of as we're attenuating the reference signal or the noise signal instead of boosting the system signal. And it is interesting can you save that one and show all of them together, Oscar? To see that if you don't consider all of these numerical analysis tools that I'm sharing, like you would expect all of these measurements to be pretty similar. Like they're just swapping the cables and with a little bit of noise somewhere. And you would think that all of these measurements would be either the bell curve up or bell curve down, and that's it. There's nothing else beyond that. But it is not. Like there's an underestimation on measurements 3 and 4, and an odd behavior on the coherence of measurements 1 and 2. The coherence values are different among themselves even. So it's an interesting approach to understanding all of these situations. All right, let's keep going to more interesting things. So now I'm going to share on this iPad. All right. So there's a fundamental problem on transfer function measurements, and is this one. What might be the reason behind the difference between these two measurements? Here's a measurement of a waveform. This is the input waveform. This is the output waveform. This is the magnitude and phase of that. And this is the input waveform and output waveform. And this is the magnitude and phase of that measurement. So this one is clearly super clean, and this is super messed up. What is the reason behind that? Well, it's a fundamental problem that I don't see very often addressed. And I see on a different node, but not exactly on this one. And it is the fact that convolution expands naturally the dimension where it is applied. That means that if you apply a filter to a signal, the signal is going to be longer. But it's just the case because of the way filters work. They delay signals in time or affect their time relationships and expand the length of the signal. And because of that, sort of the output measurement block should be longer than the input measurement block. But because we're doing an estimation where we have fixed block lengths, then like the input and the output have the same length, and there's a tiny tail that is missing from the output. And that is sort of this part. There's an input signal, and we stop the signal, there's an output section that still has some signal. So filtering expands time, and if you think about it in the time domain, in the frequency domain, it actually also works. Like a product of frequencies or spectra is also expanding time. And how much is time expanded? Well, it is expanded exactly by the length of the impulse response. And it's an interesting thing because every measurement is going to be contaminated by the length of the impulse response, simply because the current block of measurement is going to be part of the next block somehow. And the current block, the last part, and the exactly a length of an impulse response of the input block is going to contaminate the output block of the next signal. And it is just sort of the way it is. There are ways of avoiding this, sort of like having an intermittent noise, and then it should be possible to improve that situation, but it is an often overlooked problem, and it is seen much more in different cases. As we talk about reverberation, for example, and we say, oh, reverberation affects coherence, and it's exactly the same problem because the input block, when converted by the process to the output block, is much longer than the input block. And because of that, the comparison between those two is no longer like that accurate. It is just missing a lot of information. And in an extreme case, the analysis buffer, the time domain block that we have access to, could be smaller than the impulse response itself. And then the measurement, well, basically means nothing in the sense that the impulse response itself doesn't fit into the analysis window. And other people have talked extensively about this, like Merlin and Magoo. They have shown how these time records, as they are known in the FFT, affect all of this. But I wanted to show how this is so problematic from the estimation point of view, how averaging all of these values, which are the reason behind that initial transfer function that was shifting slightly or was erratic to some extent, why that is happening is because of these type of things. All right, so again, I like to repeat some important slides. The question about coherence is always why the estimation of the self spectra and the estimation of the cross spectra do not converge to the self spectra and cross spectra. Why these two things are different. All right. Whew. Just a second. I have a tiny problem. If there's any questions at this point. My battery died. All right. So a lot of people like to talk about like contamination of noise, of all of these things, but I wanted to show some effects of other things that are not commonly understood. And it's like the testing signal itself can have a huge effect on the behavior of the measurement and the coherence, because we're working with these analysis blocks that could potentially call some relationships through time. And also because distortion, which is something that affects coherence, um, could be related in time as well. It is not a completely stochastic process. It's not something that happens randomly. There's certain signal and that produces some distortion and that produces some byproduct on the spectrum, an expansion of the spectral content that has specific relationships across all of these. So let's check that one. Let's check that one out. So when you have random noise, there's no periodicity. The error is not the error that is related to the window length, which is what we just saw converges. And the spectrum is sort of predictable, but that is because we use, it's not predictable, and that is why we use the spectral density. In pseudo-random noise, which is also an option on some of these measurement tools, there's the spectrum is built from the spectral definition, or the noise is built from the spectral definition. And that naturally creates some temporal relationships, and that naturally arises the possibility of having a predictable spectrum. But it also comes with some problems. So let me share really quickly that. I think I'm gonna show only this guy. Oh, sorry, this is measurement. All right. So this should be working. Okay. Oh, technical problem. One, two. Oh, okay. I see what is happening. Sorry, guys, just a second. Input, CD, output, sum. Okay. Let's remove this. What is happening here? Just a second, please. Just a second. Three and four. Here. Ah! Test. Merly, if you have any questions for me or anything, let me know. I'm just trying to understand why this is not doing what it's supposed to do.
Yeah, that's completely understandable. That's always the challenge with these practical demonstrations. So take your time. All is good. We see Guillaume rose his hand. So Guillaume, please make use of the chat to ask your question.
Yes, please go ahead. I'm listening. I'm multitasking.
That's fine. I'm wasting. So He is wondering whether the application that you showed at the beginning of the webinar with the filters and the spirals, the Heiser spirals,
That was actually done by myself.
whether
I,
that's
I don't have
available
any
for
problem to share
download.
with it.
Um,
I guess if you text me on Facebook or something, I can share it. It's not like it's not available for download in any specific way or anything, but I don't mind sharing. It's just something that I did on a weekend, so it's fine.
okay, so Guillaume, please reach out to Juan Sierra. Any other questions that people might have at this point?
Oh, I think I understand what is happening. Finally. I need to stop this one. 1 and 2. Any other questions?
Not at this time.
All right, got it. Got it here. TUT process input 4. Okay, finally. Sorry about that.
No
So
worries.
are
We're
you
back in
guys seeing this
business.
one, right?
Yeah, we can see
Sorry.
your screen. Low pass
Okay,
filter.
so here is just a regular transfer function. If we average through time, we get just a low pass filter and it's working fine, blah, blah, blah. We have a lack of coherence in this case because there's no signal, so the estimation doesn't have any tools to actually average things out. And that is just very like a normal situation. Uh, and we have some error, and that is this bounciness. This is the same thing that I was showing before. That is because of the length of the input response, which is sort of a little bit longer input response than what you would see on just a typical filter. It's like an 8-order low-pass filter, so it has a long input response. Okay, so let's use a pseudo-random noise generator. Let's use 512, and let's go here, 512. So the pseudo-random noise has this type of spectrum. This is not the type of spectrum it has. 512 complex spectrum 512. Okay. And it has a perfect spectrum because it is generated by saying, okay, we're going to produce this frequency with a random phase at this amplitude. So it has all of these frequencies, but it always has those frequencies and it's periodic in that sense. And because of that, then the transfer function creates like time domain relationships that hold across time. And you can see that this is not bouncing anymore. This part is bouncing because the estimation is not good, because it doesn't have any signal. But this part is not bouncing in any way, and that is making the estimation converge exactly to that. So even if I estimate in 1 second long, it is not going to change, and the coherence is going to show a perfect value. So it's very tricky to talk about things related to coherence when you're not foreseeing all of these effects, because this is a perfect measurement from, like, if you see only the trace and you don't understand what it is being done, you would say, well, the filter is actually doing that because, well, because the coherence is one. So apparently it has perfect relationship between input and output. And that is sort of like a weird side effect that comes from using a pseudo-random noise that builds time relationships across different blocks. In particular, if the block analysis, my time analysis is 512, and my noise is also 512. So I guess you guys cannot see exactly that, but I'm going to change here to another one, and then it, the analysis window has less information, has more information than the spectrum that I'm using, showing again that the spectrum, even though it's noise, it doesn't have all the frequencies. Uh, Let me stop share this, and I'm going to share the whole thing. Okay. So if I go to these properties, then changing the FFT length, and how it is related to the analysis window or the spectral length of the noise, which is 512 in this case, it is going to build all of these relationships. Even if I do 32K, which is pretty good, and I then go here to 32K, you would say, oh, everything's fine. But sort of, if I start distorting this signal, then these time relationships are going to become sort of the same in every block. And then it's going to be seen by this analysis tool as a okay. So I added some distortion to that, and let's do no. You see that there's some bounciness, but like
You're
it
you're
is
not
totally.
sharing you're not sharing your screen at this point.
I'm not. Oh, sorry.
No. So you have to pick off where you went with the distortion.
Sorry.
All good.
So I'm adding some distortion, and you can see some problems on this thing, but just to accentuate that a little bit, I'm going to go to 8K, and the signal generator is also going to be 8K with a pseudo random noise. And if I average through time, coherence is fine, but you can see that like this is not the right shape of the filter or anything. It's just that these time relationships are being preserved through different blocks. So the system is thinking that those are part of the analysis window. It's an interesting like problem when you're trying to analyze distortion, because you need to make sure that like your noise sources are correctly defined, that um, your coherence is expressing what it's intended to express. It is actually showing the contamination at the output. And even in that case, the definition of the signal that you're using, if I was using white noise, for example, it would be completely different. Like the behavior of the system would be different, because distortion is a byproduct where the behavior is dependent on the signal. And because of that, then it's hard to say things about coherence. Like you need to really be sure about what that your conditions are exactly fine. And that is sort of what we try to do with M noise, is sort of to make sure that the coherence is directly related only to one specific factor, to make sure that its meaning is actually what it is intended to be. Um, so let me share once again this guy. And I'm just finishing up over here. So, okay, so we just had that the effects of testing signals on coherence are also important. It's important to understand how these relationships are being built through time on these analysis windows. And more problems, well, distortion, because it generates interfrequency relationships. Like if you feed 1K, then you're going to have some byproducts of that in 2, 3, 4, etc., kilohertz. Then it expands the spectrum. And if you're using noise to analyze this transfer function, then it is not going to build a relationship between that frequency and itself, but with that frequency and another frequency. And if the random noise that you're using is pseudo random, and you have like a specific block size and everything converges into a set of problems, then your measurement is no longer what you're intending to measure. So these relationship between frequencies can be exact, and then they can be interpreted as a linear part of the system, because it's just, well, this frequency is entering and you're having an output that has this different phase relationship and magnitude relationship, and there's a black box approach to this understanding. So we don't know how that is happening, but it is happening. And if it is happening in a constant manner, it's happening converging through all of the estimations, then it is just going to give a good coherence. It's like the natural effect of the mathematics behind it. So a pseudo-random noise could produce a constant error and will converge probably to an erroneous value, as I showed before. If the signal is random, the error might converge, but how it will affect the coherence depends on the test signal, on the distortion type. It affects a lot of things. You might even think about a noise signal that is just 1 minus 1, 1 minus 1, or in a random manner. That is a white noise signal. And if you feed that through some distortion algorithm that just has some non-linearity, it is actually not going to show any distortion, because one let's say we feed that to a system that is raising that signal to the square, no, to a power of 3, let's say. So 1 to the 3 is just, to the cube is just going to be 1, and minus 1 to the cube is just going to be minus 1. So it's an interesting signal because it cannot be distorted in that way. And because it cannot be distorted, it won't show on the transfer function measurement because it's not happening. So the selection of the signal, or the design of the signal, even as it happens with M noise, is very, very important. So there are special cases where the coherence might not even detect distortion if the test signal is not appropriate, because the effects of the distortion are by definition related to the test signal. So a little bit of conclusion on this side is, well, yeah, coherence is an indicator of the degree of linearity of the system, and a huge but its interpretation has multiple factors, and sometimes just too many. It's complicated to be sure that your measurement is clean enough to say something entirely useful about coherence. You can say, yes, this coherence is dropping because there's a comb filter. And comb filters, in theory, they don't actually, they don't, they shouldn't damage coherence in the sense that it's just a linear and time invariant system. The reason why it affects it is because many times comb filters are outside of the analysis window because it has many reflections, or because the signal is not even present. You cannot analyze something that is like, you feed this frequency and you have nothing at the output. But from the numerical analysis point of view, it affects coherence in that sense. But from a symbolic analysis, it is just a linear and time invariant system. So there's this mismatch between the reality and the theory, in the sense that when you measure that in reality, you need to have some signal to say something about it. But in the mathematical and symbolic sense, you know that just a reflection is just some special type of filter that can completely be described as a linear and time invariant system. So the coherence is dropping, but it is not actually the degree of linearity of the system. It's just that the measurement tool is not able to quantify that linearity correctly because there's no signal. So the most important thing to understand is how to compute this, how these averages are being computed, and how this measurement tool is limited by its reality. It's limited by computation and by approximations. So if we understand how the measurement was done, what were the conditions, what was the test signal used, what was the system like to some extent, and how was the contamination, either input and output, then we can say something about coherence. Then we can say something about coherent power versus non-coherent power, or let's talk about signal to noise ratio to some extent. So because of all of that, it must be used very, very carefully, but hopefully you know now what it actually is and how it is actually behaving. I think that's pretty much it. And if you guys have any other questions, sorry for the delay. I know it was supposed to be 1 hour long, but this was a tough one to explain. So let me know if anything else is needed. Let me stop this thing.
Thank you, Juan Sierra. Super, super, super useful. So if anyone has any questions for Juan Sierra, be sure to make use of the chat, and we'll try to answer your questions to the best of our ability.
I really suggest that, like, it's a little bit of a hard thing to completely understand. So if you check this video later on YouTube and pause through some of the math and like try to figure out what he's actually saying, I think it could be really useful if you really want to understand all of this. Just a piece of advice.
Yep.
All right. If
Well,
any questions, I'm happy to help. Or if it's far from.
so
Why should
Guillaume,
we watch it again?
Guillaume comments you and said that it was great, and he thanks you very much. But he also realized that school is a long time ago, and he should definitely watch it again. And that's good. That's good. That's how we learn. We learn by repeating.
Also, don't
Excellent.
feel bad because a lot of this is not actually taught very often. It is not shown like the insights of transfer function measurements in that way. So just take it one step at a time.
Agreed. That being said, if I'm not mistaken, Juan, Sierra, we are fortunate to have you join us again this Friday.
Yes.
With something completely different.
Yes,
Something
I mean
entirely different.
it has an interesting connection in the way averages are being understood in that process in the project, but it is different, absolutely.
Right. Okay, well, thank you very much, Juan Sierra, for doing this wonderful webinar on coherence. And that means that, as always, a recording of today's webinar can be found on our YouTube channel, Thinking Sound, within the next couple of hours or so. And like I mentioned before, Juan Sierra will join us again on Friday, where he will discuss plug-and-play multi-channel systems, more specifically the AMI system. So be sure to join us this Friday. And without further ado, please stay safe, please stay healthy. Thank you, Juan Sierra, once more. Thank you, Oscar, who was also
Thank you,
instrumental in today's
Dali.
webinar. And see you Friday, hopefully. Bye-bye.
Thank you all. Bye.